Chapter 3.5, Graphs of Rational Functions and Their Applications. Okay, the definition of rational functions is really simple. It is a fraction. Rational number means fraction, right? Rational numbers, irrational numbers. So rational numbers, fractions is called a rational number. So rational function is a function whose numerator and denominator is polynomial. So it's a fraction. So for example, y equals 1 over x. So, x, the variable x is in the denominator, so it's a polynomial, right? So usually the denominator contains x, then it's a rational function. Or it can be also y equals, x squared plus x over, plus 1 over something like this, x plus 1, like this. So both numerators are polynomial, contains variable x, or the denominator contains variable x. So in this case, we must be careful that fractions, the restriction of a fraction is the denominator cannot be equal to 0, right? So for example, 2 over 0, this is undefined, which means because the denominator is 0. The denominator is 0. So the domain, the value, the set of all the x values will be all real numbers except those x values that makes the denominator 0, right? So in this case, we always make sure that the denominator cannot be equal to 0. Okay, the denominator cannot be equal to 0. Okay, so x value can be anything except those x value, those x values that the denominator makes 0. Okay, so and then also the numerator depends on the function of the numerator. So the domain, first of all, domain cannot have all the x values that makes the denominator 0 at first. All right. Okay, so let's try a function y equals 1 over x. Okay, the graph of this is, I think I have mentioned this before. Okay, the graph of this is really simple. And then we're gonna put, okay, when we graph a function, always use 0, when x equals 0, 1, 2, or -1, -2, and close to zeros. So if x equals 0, what happens? It's undefined, right? There's no y value when x equals 0. How about x equals 1? If x equals 1, then okay, let me draw a little data type table. So when x equals 0 is undefined. And then if x equals 1, then 1 over x is equal to what? 1, right? 1. So it is 1. And if x equals 2, let's look at this, what happens. X equals 2, then 1 over 2, right? 1 over 2 is just 1 over 2, right? So, getting close, the y value is now decreased by half. And if x equals 3 is 1/3, right? 1/3, and so on. It's getting, the y value is getting smaller, but approaching 0, right? Approaching 0. So x approaches infinity, then y approaches 0, right? 0. Getting close to 0. Not 0, but getting close to 0. Smaller, right? Smaller. Getting smaller and close to 0, right? 0. When x approaches infinity, right? Okay, how about x is 1/2? X is 1/2, then reciprocal of 1/2 is 2, right? 2. So 1/2, then it will be 2, right? 2. And 1/3, it will be 3. So as, can you see it? The graph looks like this. And if x -1, -2, and so on, then the graph looks like this. Okay. So it's really important. Remember the graph of 1 over x, because it's really simple. The right end, as x increases infinity, then the y value gets close to 0. if x gets to 0 from the right side, then the y value gets positive infinity. Can you see it? So in this case, as x approaches 0 from the right, from the right, then y approaches infinity. How about the right end of this graph? As x approaches infinity, then what? Then y approaches 0. I will use an arrow. Arrow indicates an approach. Even this one, as x approaches negative infinity, then what? Y approaches 0 at 0. How about this one? Going down. This means as x approaches 0 from the left, right? From the left. Y approaches where? Negative infinity. So look at the arrow. Look at the arrow of the end of each graph. Then we can see, where it's going. Is it positive infinity, negative infinity? So from this, here's a very, very important concept. This arrow and this arrow are approaching what? The x-axis, right? It's approaching the x-axis. So we call this horizontal asymptote. We call this what? Horizontal asymptote. Asymptote. How about the y-axis? Look at the y-axis. And the end of this graph and end of this graph are approaching the y-axis, right? So we call this vertical asymptote. Vertical asymptote. Okay, so vertical asymptote and horizontal asymptotes are, the horizontal line and vertical line. Horizontal line is so called horizontal asymptote if graph approaches that line. Vertical asymptote is a vertical line where the graph approaches that vertical line. So let's say here is a horizontal line. Let me draw a dotted horizontal line, and the value of y is 3. Okay, let's say a graph looks like this. Graph looks like this, and this end is approaching where? The horizontal dotted line, right? So we call this horizontal asymptote. Horizontal asymptote. Asymptote. So since it's a horizontal line, the equation of the horizontal line is y equals 3. Can you see it? How about this end? Let's say this end is going down like this. Then the vertical line. This vertical line is the vertical asymptote, right? Vertical asymptote. And then since this is a y-axis, the y value, y-axis, right? Y-axis crossing the x equals 0. So the equation of the vertical asymptote is x equals 0, right? X equals 0. Can you see it? Horizontal asymptote, vertical asymptote. We can try a little more example like this. X-axis, y-axis. And let's say, okay, also there is a horizontal line. And then let's say the graph looks like this, coming down like this, and then going up, and then approaching the horizontal axis like this. So in that case, this is a horizontal asymptote. Let me write horizontal asymptote. Okay. So the equation of this horizontal line is, let's say this is number 2. The y value is 2. Then since this horizontal asymptote, you can write the equation as x equals 2. Can you see it? It's horizontal asymptote. All right. So make sure the end of a graph is approaching a line, then horizontal line, then that is the horizontal asymptote. How about the vertical asymptote? Okay, and this graph shows both the horizontal asymptote and the vertical asymptote. Look at this. this end of the graph and this end of the graph are approaching the horizontal line, right? This horizontal line. So this is horizontal asymptote, h dot a. Let me write it HA, horizontal asymptote, right? Then what's the equation? Equation is y equals y value. This horizontal line passing through the y-axis at 2, right? At 2. So that's horizontal asymptotes. How about this one? This end and this end is going up, right? Going all the way up, and it's approaching this vertical line. So we call this vertical asymptote. And this equation of this vertical asymptote is x equals the x value, because the vertical line is passing through the x-axis. This one, right? So x equals 1. Can you see it? Can you find the vertical asymptote or horizontal asymptotes? All right, then let's find out the equation of vertical asymptote and horizontal asymptote of a rational function. All right, before we do that, let me explain how we find the vertical asymptote. Okay, so in order to find the vertical asymptotes, okay, let's say the function f of x equals p of x over q of x. All right, so when we make the denominator 0, set the denominator equal to 0, then all those x values will make it vertical asymptote. All right, so vertical asymptote, where is the vertical asymptote? All right, so in order to get this vertical asymptote, x, set the denominator equal to 0. Then all those x values are vertical asymptotes. Okay, vertical asymptotes. All right, so let's try this. So in this case, we want to find the vertical asymptote. So set the denominator equal to 0. Denominator equal to 0, and then let's find x. Then those x values are the vertical asymptotes, so that there's no y value for those x values. So we're gonna set what? Set the denominator equal to 0. All right, so I'm gonna make x plus 1 equal to 0. Then x squared is negative 1. Look at this. For the real number, x squared cannot be negative 1, so, right? So there's no such values. Right? There is no x values, right? No x values making x squared equals negative 1, right? So in this case, denominator cannot be equal to 0. So therefore there is no vertical asymptote. No vertical asymptote. Can you see it? So if we can find any x value that makes the denominator 0, then that's the vertical asymptote. But in this case, there's no vertical asymptote. Okay, how about the next function? I'm going to make the denominator equal to 0. So let's make it 0. Then we can factor this one, x times x, 2 times 3. And the minus sign goes here, so that this product is 2x, and this product is negative 3x, and the sum is negative x, right? This is same as the second term. So we can rewrite it. X plus 2, x minus 3 is equal to 0. So product of this binomial is 0, so set each factor equal to 0 so that we can find x values, right? So x is negative 2, and from the second factor, x equals 3. So we found two x values. So if x is negative 2 and negative 3, then the denominator will become 0, right? So therefore, the vertical asymptotes. So the vertical asymptotes, there are two of them. X equals negative 2 and x equals 3. All right? So when you graph this, the graph, well, we can graph it later. But for this one, we know that two x values will make up the vertical asymptotes. All right. So probably the graph looks like this. If you use a graphing calculator at this moment, So when x equals negative 2, negative 1, negative 2, then this is a vertical asymptote. When x equals 3, 1, 2, 3 is a vertical asymptote. So graph, end of a graph will approach these two vertical lines. So if you use a graphing calculator, then probably it looks like this. It looks like this. So as you see this end is approaching where? This vertical line, right? And there's another one inside these two vertical lines. It looks like this. So this end is approaching this vertical line, and this one is approaching this vertical line, and there's another one, and it looks more complicated, right? So it looks like, so there are two vertical lines where graph of this function approaching. All right, can you see it? Okay, here is a very useful theorem, behavior near a vertical asymptote theorem. Okay, this is really simple. Okay, let's say f of x is a rational function, so that the denominator looks like this. Okay, this is the denominator, right? And this denominator is x minus a to the nth power. So the exponent is n. And we know that x cannot be equal to 0, right? So, a, right? A cannot be, the denominator cannot be equal to 0. So, x can be any real number, but a. So the vertical asymptote, in this case, the vertical asymptote is x equals a, right? So there's no y value when x equals a. And then in this case, if the exponent is even or odd, so let's say n is odd number, then let's say here's a variable. Okay, let me change this one. Let me change this. This is not the x-axis. Vertical asymptote, right? Let's say this is the vertical asymptote, a. Okay, vertical asymptote. Then the graph looks like this. If one is on the right side like this, and the other one is on the other side like this. Okay. Okay, or it can be like this. So let's say this is a vertical asymptote. Okay, vertical asymptote, and if it's on the upper left corner like this, then the other one is on the right side, lower right corner. So this is the graph. Can you see it? So if the the exponent is odd, it looks like this. If it is n is even, if it's even, then what? Even number, when you square a positive number or negative number, the result is always positive, right? So if the vertical asymptote is a, then both graphs are above the line, or if you negate it, then both graphs are below the line like this. Can you see it? Like this. So it's very useful. Make sure the denominator is raised to the nth power, and then if n is odd, then based on the vertical line, one is on the right side, one is on the other side in opposite direction. And if n is even, then both graphs are in the same locations, above the x-axis, above the the horizontal line or below the horizontal line. So let's try this example. Okay, as you see this, the exponent of this x minus 2 in the denominator is 1. So we know that x equals 2 is an asymptote, vertical asymptote, and x equals 5 is a vertical asymptote, right? Vertical asymptotes. These are the vertical asymptotes. So let me draw two vertical asymptotes. One goes when x equals 2, 3, 4, 5. Another one goes to x equals 5. All right. And then since this is 1, okay, let's say when x equals 5, the exponent is 2, right? 2. This is even, right? Even. So the graph around this vertical line will be in the same line, above or below, right? So let's say if x equals 6, let's see the sign. Okay, let's see find out the sign. The sign is it positive? Okay, look at this. The numerator, if x equals 6, then the numerator is positive. The denominator is positive times 6 is positive, right? So it's positive. So it's gotta be on this side. All right. All right. Then for the left one, for the left of this vertical line, we should have the same side, above the line, above the horizontal line. Okay. How about if x equals 0? What happens if x equals 0? Then the numerator is 0, so it's gotta be 0, right? Oh, sorry. X equals 0, then y is 0. Okay, what I'm doing is for the horizontal number line, here's the vertical line is when x equals 2 and 5, right? And even when x equals 0, okay, we will find out the positive, the sign of the y values. So if x equals greater than 5 is positive, if x equals 0 is positive, and then if we go on all the way to the left, then that is a positive, right? And then if x equals between 0 and 2, okay, let's use 1. Okay, if x equals 1, then 1 is positive, right? Over 1 is negative times positive. So this part is negative. And if x equals between 2 and 5, let's say x equals 3, then it should be positive. Okay, anyway, numerator is positive, denominator is positive times positive. So it's positive, right? Positive. So based on this information and the behavior theorem, near vertical asymptote theorem, we can graph it. So since 5, the vertical asymptote when x equals 5 has even, 2 is even, right? Even exponent. It's going to be something like this. Something like this. Because it must have both. It must have, this graph should be on the same side, above the line, right? Above the line. Make sense? All right. And then for when x equals, for the vertical asymptote 2, they are in a different side, right? Different side. So since when x is less than 2, it's going to be something like this. It's on the bottom side, right? So the other side, the other end, graph of the other end should be on the other side like this. Can you see it? And it's going up and then something like this. All right. So this is the graph looks like this. Can you see it? Okay, we will explain more about this. So important thing is when n is even, then graphs are on the same side, either above or below the horizontal line. If n is odd number, then if one is on the right side, above, then the other one is below. If one is on the left, above, then the other one is on the below, right, under the horizontal line. Here's also a very, very important theorem about the horizontal asymptotes. Okay, let's say the rational function f of x has numerator and denominator like this. So numerator is a polynomial whose degree is n, and the leading coefficient is a sub n, right? And the denominator is also a polynomial whose degree, the degree means the largest exponent in this denominator, and the leading coefficient is bm, right? So the horizontal asymptote always depends on, it comes from the, by comparing the exponent. Okay, compare the exponent. the degree of the numerator and the degree of the denominator. So look at this. If the degree of the denominator like this, do you remember y equals 1 over x? Okay, in this case, the degree of the denominator is 1 and the numerator is 0, right? So the graph is what? The graph looks like this, right? So this is the horizontal asymptote. The x-axis, horizontal asymptote is the x-axis, isn't it? Okay, y equals 0, right? Y equals 0. Do you remember this part? The graph of 1 over x is always like this, always. So x-axis and y-axis. Then the horizontal asymptote is x-axis. All right? So as an example of this, if the degree of the denominator is greater, then always the horizontal asymptote is the x-axis. Always. So equation of the horizontal asymptote is y equals 0, right? So don't forget this. This is really important. And then if the degree are the same, x-axis and degree of the denominator and the numerators are the same, then the horizontal asymptote is really simple, the leading coefficients. So the leading coefficient of the numerator over the leading coefficient of the denominator. Really simple, right? Really simple. Like this. So that's the horizontal asymptotes. All right. Okay. How about if the numerator's degree is greater this time? The numerator's degree is greater, then there is no horizontal asymptote. No, not at all. But there is slant asymptote, different asymptote. It's not a horizontal asymptote. Slant is what? It's not horizontal, right? In this case. So there are three types of three cases to find the horizontal asymptotes. So by comparing the degree of the numerator and the denominator. All right, then let's try example. Okay, let's find horizontal asymptote. Horizontal asymptote, right? So compare the degree. So the degree of the denominator, what do we do? Compare, right? Compare the degrees, right, of the numerator and the denominator. And the denominator. Okay, so now the denominator is 2, right? The degree is 2, right? 2 is greater than 1. This means the denominator's degree is greater than the numerator, right? So the horizontal asymptote equals what? The x-axis. Okay, x-axis. Simple, right? Simple. Okay, how about this one? The horizontal asymptote is, the degrees are the same. The degrees are the same. Same degree, right? Same degree. Same degrees. Same degree. So what? The horizontal asymptote y equals the leading coefficients, 4 over 3. Isn't it really simple? Okay, how about this one? 3 is greater than 1, right? 3 is greater than 1. So degree of the numerator is not greater, right? Greater than the denominator, degree of the denominator. Right? Because 3 is greater than 1, right? So, therefore, there's no horizontal asymptote. All right? So, if we apply this information so that we can graph it, actually. Graph it, not precisely, but we can graph it approximately. Okay, here is general procedure, general steps for graphing rational functions. Okay, this is really important because we already learned this one earlier. So let's summarize this. Okay, first, find the vertical asymptote and the horizontal asymptote. So how do you find the vertical asymptotes? Set the denominator equal to what? 0, right? Equal to 0. and then draw a vertical line at that x values. And then horizontal asymptote, what do we do? Check the degree, right? So check, compare the degrees. Remember the degrees. If the denominator's degree is greater than the degree of the numerator, then always the horizontal asymptote is the x-axis. Okay, and then find the x-intercept and the y-intercept. How do you find the y-intercept? We just set x equals 0 so that we can find the y value. And how do you find the y-intercept? In this case, the numerators get, we want to set y equals 0, right? So this implies that the numerator, set the numerator equal to 0. Numerator equal to 0. Because, 0 over x is 0, right? So we will set always the numerator equal to 0 so that the y value will be 0. Okay? So set numerator equal to 0 so that we can find the x-intercept. So those are the x-intercepts. All right, so also check the its symmetry. The function is symmetry with respect to the y-axis or the origin. So to check the y-axis, that means when x is plugged with negative sign, then always we'll have the same y value, right? So if it satisfies like this, then the graph is symmetric with respect to the y-axis. How about the origin? Origin means if we plug in negative x, then the result is negative y, right? That is the, then if we have something like this, then the graph should be, the graph will be symmetric with respect to the origin. So that is how we check these things. And also, this is also important. Now check additional points between or beyond the vertical asymptote and the x-intercept. Okay, this means we know the vertical asymptote, right? Vertical asymptote. And let's say there is an x-intercept, like x-intercept like this. Then this is x-axis. This means for each interval, in this case, the interval is less than this vertical asymptote, and between this, so here's the interval 1, interval 2, interval 3, 4, and 5, beyond this line, right? So for each interval, we will check whether the graph is positive or negative. If positive, then the graph is above the line, above the horizontal line. And then if it's negative, the y value is negative, then below the horizontal line. Can you see it? So this is really, really important part. So if this is positive, negative, just an example, negative, and this positive, and this is, let's say, negative, right? Negative, then the graph looks like this. It should be something like this, and maybe like this, right? It depends. So it's really important to check additional points so that we can find out the sign of y. So check the signs of f of x for each interval. The interval means the x interval, okay? X intervals for each interval. All right. Now behavior near asymptote. Remember, if the denominator is in the factor form, if the denominator, look at this, if the denominator is a factored form, right? So check this one. So we know that the graph is the side, the near the asymptote, right? Remember, near the asymptote, the graph is both above the line, above the horizontal asymptote, or both are below the horizontal asymptote. Remember, right? Remember this guy? Or they are on different side, right? Different side like this. Okay, so in that case, n is odd, n is even, right? N is even, then it looks like this. If n is odd, it looks like this. Okay, so based on this information collected, obtained from step 1 to 5, we can sketch the graph. Really, really useful information. All right, then let's sketch a graph of this function. Okay, first we need to check the asymptote. So vertical asymptote. Let's find the vertical asymptote. How do you find it? Set the denominator equal to 0. Denominator equal to 0 and then find x. And the denominator is what? X squared plus 3, right? Then this one is x squared is negative 3. So it cannot happen. So we cannot find any x values. So no x values, right? No x values that satisfies this inequality, this equation. So there is no vertical asymptote. It's really important. No vertical asymptote, because x, the denominator cannot be 0, because no matter what x value is, this one is always positive, cannot be negative or even 0. Okay, how about the horizontal asymptote? Compare the degree, right? Compare. Check the degrees. So the degree are the same, right? Same degree. So this one has the same degree. So what? The horizontal asymptote is what? Y equals the leading coefficient, 2 over 1, which is 2, right? 2. So y equals 2 is the horizontal asymptote. All right? Okay, now number 2. Now we can check the intercept. Let's find the x-intercept and y-intercept. Okay, let's find out intercept. So, okay, let's find the y-intercept. How do you find the y-intercept? Set the other variable x equal to 0. Okay, so f of 0 is what? 0, 2 times 0 squared minus 18 over 0 squared plus 3, then negative 18 over 3. So negative 6, right? So the y-intercept is when x equals 0, y is negative 6. So we're going to plot this point for the y-intercept. How about the x-intercept? All right. Set the other variable y equal to 0. That means set the numerator, right, equals 0. So what's the numerator? 2x squared minus 18. So make it 0. Then 2x squared equals 18. Then x squared equals 9. So that x equals plus or minus square root of 9. So this means there are two x-intercepts, x equals 3 or negative 3, right? X-intercept. And then number 3. Number 3 is asymptotes, the symmetry, right? Symmetry. So, let's plug in symmetry. So let's plug in negative x. And then let's see what happens. So negative x 2 times. Look at this. The base x is, the power is 2, right? 2. So whenever we make a square of, negative square, then it's always positive, right? So it should be the same. It should be the same function, right? So this one is equal to 2x squared minus 18 and x squared plus 3, right? So that is f of x. So this is symmetric with respect to what? To the y-axis, right? So this is symmetry. So this means symmetry with respect to the y-axis. So once we graph only the parts when x is greater than 0, then we can make it a symmetry, right? Okay, next one is additional point. Additional point is for what? For the, we're looking for the sign of the function, sign of y, so that, we know that the graph is above the horizontal asymptote. I mean, the x-axis and the y-axis. So in this case, let's draw all the vertical asymptote and the x-intercept. So there's no vertical asymptote, so in this case it's okay. And x-intercept is x equals 3 and -3, right? All right, so let's find out the sign of the function. So if x is -3, look at this, write it here. I'm going to find out the sign, right? Sign. So let's use x equals. So there are 3 intervals. So 1, 2, 3 intervals. So for interval 1, we're going to set x equals what? Let's use -4. Then what is the sign? -4. So -4, so 2. Okay, so the numerator is -4 squared is 16, right? 16 times 2, and then -18 is positive. And the denominator is also positive. Denominator is always positive, right? So the result is positive. So this area is the positive. If x equals between these two, let's use 0 or anything is fine, right? So let's use x equals 0. We already found when x equals 0. If x equals 0, that is negative over positive is negative, right? Negative part. And then third interval. So if x equals 4, this is symmetry, right? Symmetry, so it's got to be positive. Okay, let's try x equals 4. Then the numerator is what? Positive. Denominator is positive. So it's positive. So this is positive. All right, then let's graph it. So the denominator, x equals x squared, right? X squared. So when x equals 0, same side, right? Number 5. Behavior near what? Asymptote. So in this case, there's no vertical asymptote, so that is fine. But as you see this in x squared, actually this is not a vertical asymptote, so there's no vertical asymptote, so it's okay. However, if we compare with the horizontal asymptote, there's horizontal asymptote, right? The horizontal asymptote is y equals 2. So in that case, if y equals 2, then is there any x value? If a graph across the horizontal asymptote, then we should have x value, right? But for the horizontal asymptote, that is y equals 2, right? So if you rewrite the function, then y equals, the function is x squared, 2x squared minus 18 over x squared plus 3, right? So if you set y equals 2, then what happens? We just want to compare whether there is x value that makes, when the graph across the y equals 2. Then this one looks like, 2 times x squared plus 3, right? Equal to x squared minus 18. Then 2x squared, just checking. Don't worry about this one. Look at this. If this one cancel out, then 6 equals -18. So there is no y values, right? No y values. What do you mean by this? We cannot find any x value, right? We cannot any x value, right? We cannot any x value so that the graph crosses y equals 2, right? There's no solution, means no x values that makes the expression y equals 2, right? Can you see it? All right, so this means the graph does not cross the horizontal asymptote. It does not cross the horizontal asymptote. So keep in mind this and then graph it. All right, so look at this. This is x-axis and the y-axis. All right, the horizontal, there's no vertical asymptote, but there's a horizontal asymptote. What's the horizontal asymptote? Y equals 2, right? So y equals 2. And then what are the x-intercepts? 3 and negative 3. So 1, 2, 3, and negative 3. And what's the y-intercept? That is 6. Let's say this is 6, negative 6. The y-intercept is negative 6, right? Negative 6. All right. And then the signs. The signs are negative if it's between negative 3 and 3, right? Negative. And if x is less than negative 3, then this is positive. So this horizontal asymptote. So we can draw cross this one, right? And then like this. And then somehow draw something like this. Can you see it? So this is horizontal asymptote. Horizontal asymptote. And this part is positive. So between this is negative, right? And from this one is positive. This horizontal asymptote. And this one never crossed the y-axis. I'm so sorry. The horizontal asymptote, right? Never crossed the horizontal asymptote because as you see this, there's no x value that makes this equation 2, right? 2. So it's gotta be something like this. And then draw it smooth. And then this is symmetry across the y-axis, right? Symmetry across the y-axis. So it's we must have same graph on the left side of this y-axis, like this. So let me draw this clearly. Okay, so the graph looks like this, and then I'll try next one. Okay, we will do the same step, follow the same steps, and then to sketch this as h of x. Okay, first, okay, let's find the asymptote. All right, how about the vertical asymptote? We're gonna set the denominator equal to 0, right? Set the denominator equal to 0, so x squared plus x minus 2 is 0. Then x times x, 1 times 2, negative sign goes here. So that this one is x minus 1, x plus 2 equals 0. So x is 1 or x is negative 2. So we found two vertical asymptotes. This time there are 2 of them. How about horizontal asymptotes? Okay, check what? Check degrees, right? Degrees. So as you see this, the degrees are the same. 2 and 2, right? So same degree. Same degrees. So the horizontal asymptote y equals 1 over 1, right? 1 over 1. 1 over 1, which is 1. So y equals 1. So that's the horizontal asymptote. All right. And then let's check next one. Okay, next one can be it's a x-intercept, y-intercept. So let's find the y-intercept. The y-intercept is the easiest one because we're gonna set x equals 0, right? Set x equals 0. Then what is y value? X equals 0, right? So 0 plus 1 over 0 plus 0 minus 2. So that equals negative 1 over 2. So the x-intercept is, so the y-intercept, right? So that y-intercept is x is negative 1 over 2 and y equals 0. Okay, we found one y-intercept. How about the x-intercept? Okay, we're going to set x equals 0. In this case, set which one 0? Numerator 0, right? Numerator. And the numerator is what? Cannot be 0, right? Because x squared plus 1 is, this one is x squared is negative 1. So there's no solution, right? No solution, right? No solution. Which means, this means what? No x-intercept. Okay, in this case, there's no x-intercept. Only the y-intercept. Okay, how about symmetry? In this case, the symmetry won't work because it's neither symmetry with respect to the y-axis nor the x-axis. All right. So not symmetric, right? Because you can plug in negative x, but it doesn't make f of x or negative f of x. So not symmetric. Okay, next one is, okay, let's check the points. Okay, points between intercepts. Okay, so so the vertical asymptote is 1 and negative 2. This is 1 and negative 2. There's no x-intercept, right? No x-intercept. All right, so let's check these points. So if x equals negative 2, okay, here's interval 1, 2, and 3. For each interval, let's use x equals negative 3. Then h of negative 3 is, okay, let's look at the sign. All right, negative 3 squared is positive, right, over also positive, right? Just plug in the number, then the result is positive. Okay, for the second interval, let's use x equals 0. Then as you know, the 0. When x equals 0, what happens? X equals 0. Okay, let's find out x equals 0. Then 0 plus 1 is 1, right? 1 is positive. And then 0, 0 is negative, so negative. So we have a negative sign. All right. And then, so actually when x equals 0, look at this. The y-intercept, okay. The y-intercept, when the y-intercept is, I wrote incorrectly this one. This is not right? The y-intercept is when x equals 0, then the y value is negative 1 over 2, 0.5, right? 0.5. So that's the y-intercept. All right, and then next one, we can try the end behavior, right? So since the vertical asymptote, look at the denominator. Denominator is, it's not a perfect square, right? It's not a product of factors. So even it's a product of factors. Okay, look at this part, right? This part. So the denominator is, this one, right? X minus 1, x plus 2, right? So both exponent is even, right? These are odd. So the graph should be, one is above horizontal, the other one is below the horizontal, different side, right? So for the vertical asymptote, 1 and negative 2, the graphs are, one is up, one is below. Okay, so let's keep in mind that. How about the horizontal asymptotes? In this case, horizontal asymptotes. All right, so for the horizontal asymptotes, y equals 1, right? Horizontal asymptote means y equals 1. So if we set y equals 1, let's find out the function, x squared plus 1 over x squared plus x minus 1 minus 2. So from here, we can find x value. So let's find the x. So that means, the graph will cross y equals 1 when x equals, this value that we will find. So cross multiply, and then we can cancel out this x squared. Okay, so write down, x squared cancel out. Then x equals what? 3, right? So when x equals 3, y will be 1. So the graph will cross this point. This is horizontal asymptote. Okay, so based on this information, let's graph it. So don't get confused. Okay, x-axis, y-axis. And horizontal asymptote is what? Okay, let's use a different color. Horizontal asymptote is y equals 1, right? Y equals 1. Horizontal asymptote, y equals 1. Okay, horizontal asymptote, y equals 1. How about the vertical asymptote? 1 and negative 2, right? One and negative 2. Negative 1, negative 2. This negative 2. All right. And then we know that a graph crosses the horizontal asymptote when x equals 3. When x equals 3, it crosses this point, right? Right. And then from the vertical asymptotes, the graph is one is above, one is below, right? One is above and below. Okay. And then as you see this one, how about the number 4? The behavior, right? So if x is, okay, I didn't write it here. So for the equation, for the interval 1, that is positive. This is positive side. And between these two is negative. I forgot number 3, right? We got to number 3. So if x is greater than 1, let's say, we already did this one because when x for the number 5, right? Okay, anyway, let's try number 2. Then h of 2 is 2 squared plus, the numerator is positive always. How about the denominator? Calculate it. 2 squared is 4 plus 2 minus 2 is positive, right? It is positive. All right. So for this one, if x equals 2 is positive, but it's greater than 1, so it's got to be above, like this. All right. And then cross this one, but somewhere it's bending, so it goes to what? The horizontal asymptote. Okay. And then, so probably this part is not exactly the same, but somehow it's going down, right? Going down, and then you will get close to the horizontal asymptote. Going down, right? And then somewhere it's going approaching the horizontal asymptote. All right. And for the vertical asymptote at 1, the side should be where? The other side, this time below the horizontal asymptote. But in this case, the axis, the sign between negative 2 and 1 is negative, right? Always this is negative part. And then the the y-intercept is negative 2, right? Negative 1 over 2, y-intercept. So this is the y-intercept, negative 1 over 2. So crossing this point, okay, that is negative 1 over 2, right? Crossing this point, and then it keeps the negative sign. So it's going to be go this way. Why is it going this way? Because it should be a different, since this is above, this one should be below, right? And then maybe going somewhere and then return, going back to the this side. Why? because this is the asymptote, right? Asymptote. So it's got to go somewhere. But this one does not cross the x-axis because there's no x-intercept. No x-intercept. So the graph does not cross the x-axis. All right, how about for the interval less than -2? That's positive, right? Positive. So the only way is this guy. Why? Do you remember the behavior near the asymptote, vertical asymptote? One is in the below, right? Below. So the other one should be above, right? Above. So this one going up, so that this one should go to this way, right? So that's the graph of this rational function. Can you see it? It's kind of confused, but make sure we collect, we use all the information we got it from the step 1 to 5, and then graph it. All right, so hope you get this, and then please try more examples. Okay, now slant asymptote. Let's graph a slant asymptote. Okay, now the slant asymptote is really simple. The degree of the numerator is greater than the degree of the denominator, then there's no horizontal asymptote, but there may be a slant asymptote. So it's really simple. What you have to do is divide the numerator by the denominator, and the quotient is the slant asymptote. So something like this. When we divide 9 over 2, right? Then once we divide this 9 over 2, then this will be 4, 8, and 1. This is the quotient, so we can rewrite it like this. This will be 4 plus 1 over 2, right? This is the remainder. This is the remainder. This is the quotient. So we can write the rational expression by dividing the numerator by the denominator. Then the quotient part. The quotient part, it will be the slant asymptote. All right, so look at this. Let's divide this one. Find the slant asymptote of this function f of x. So let's divide it and then find out rewrite it in terms of this quotient plus remainder of the denominator. All right, so 2x cubed plus 5x squared. There's no x term, so put 0 and the constant. Divided by x squared plus x plus 3. Let's divide it. So x goes here, 2x goes here, so that the first term will be, the product of the first term will be 2x cubed, and the product of the second term is 2x squared. The third term is 6x, and then we subtract from top, top minus bottom, right? Then the second term, the first term is 0, the second term will be 3x squared. The next one is negative 6x. Okay, let's try more. And then the second term will be what? Plus 3, right? So multiply 3, then 3x squared plus 3x, and then plus 9. Then divide and then subtract. The first one is 0, the second part is negative 9x, and then minus 9, right? Oh, sorry. Bring one down. Bring one down. So that will be negative 8. So this is the remainder. This is the remainder, and this is the quotient, right? Quotient. And this is the remainder. Right? So the remainder, the degree of the remainder is less than the dividend, so we are done. So if we rewrite it, then this will be 2x plus 3, right? Plus the remainder is negative 9x minus 8 over the divisor. Can you see it? So in this case, look at this. The degree is 3, so we are dividing by 2, right? So this time we have a linear. So this is the slant asymptote. If this is quadratic, then the quadratic graph is the asymptote. All right, so this is the slant asymptote. Okay. So slant asymptote, so let's say, y equals 2x plus 3. So that's the slant asymptote. So if we graph it, it's going to be something like this. It's not accurate, but x-axis, y-axis. And the graph of this slant asymptote is when x equals 0, y is 3. 1, 2, 3, right? And then the slope is, if y equals 0, then if y equals 0, then x equals negative 2/3. So it's going to be somewhere over here, right? So this is the slant asymptote. Slant asymptote. That guy. Then the graph. The graph depends on, and then the graph actually, we got to do some, work. But once we refer to, graphing calculator, it's something like this. Okay. So this is the asymptote, so it's gonna go this way, and then somewhere it's changing like this, and then going like this, and this end is approaching the slant asymptote, and left end is approaching the slant asymptote like this. Okay, use the graphing calculator, then we know that the graph end of the graph, right end, far right and far left is approaching what? The slant asymptote. Okay, next one is an example of graph of rational functions with common factors. So let's say in this case the numerator is x minus 1, denominator is x minus 1. So when we factor the numerator and denominator, we can cancel out the common factor, right? But before we cancel out the common factor, what's the restriction? The denominator cannot be equal to 0, right? The denominator cannot be equal to 0. So x should not be equal to 0, and also x should not be equal to 1, right? So we keep this in mind because there's no y value when x equals 0 and 1, because this makes the denominator 0. So once we cancel this out, it looks like this, 1 over x, right? So the graph is based on 1 over x. Okay, keep in mind that the actual graph will be 1 over x, which is something like this, right? Something like this. But important thing is x cannot be equal to 0. X cannot, there's no y value when x equals 0, and there's no y value when x equals 1. So before we cross out, simplify the rational expression, we know that x cannot be equal to 1 because there's no y value when x equals 1. So this means no y value, right? No y value at x equals 1. So in this case, if x equals 1, then y equals 1, right? Y equals 1. But we will remove this part. There is a hole inside. Hole means when x equals 1, there's no y value. Make sense? So whenever a binomial is something, the common factor is removed, make sure put a hole. Okay, put a hole so that we don't include that point. So this is when x equals 1, y equals 1, right? So there's no y value when x equals 1. So it's really simple. If there's a common factor, you can remove it and then graph it, but make a hole on that when those x values are. Okay. All right, so let's sketch this function. And the numerator, we can factor the numerator and denominator, and if there are same terms, then we can, common factors, we can reduce it. So this is x times x, the 1 times 4, and the minus sign goes here, right? So that this will be x, this product is negative 4x, so the sum is negative 3x, which is same as the term in the middle. So f of x can be written again as x plus 1 times x minus 4 over, how about the denominator? X times x and 2 times 4, both negative. So both negative makes the sum of the cross multiply negative 6x, right? All right, so the denominator is the product of x minus 2 and x minus 4. So in that case, what are the restrict values? X cannot be equal to 4 because denominator, right? And then x cannot be equal to 2. So there is a hole when x equals 2 and negative 4. Well, actually, okay, when x, in this one, x minus 4 cancel out. So this means hole, right? There's a hole. Hole. How about this one? That is a vertical asymptote. Can you see it? Vertical asymptote. So if you rewrite it after simplifying, it looks like this. So as you see this, that's the vertical asymptote, isn't it? Vertical asymptote. But when x equals 4, there's no y value, so we have to put a hole when x equals 4. So the graph, you remember the graphing method? Use all the information from the graphing method. Okay, so the vertical asymptote is 2, right? 2. Vertical asymptote is 2. And is there an exact, how about vertical asymptote? How do you find the vertical asymptote? We already found it, right? X equals 2, right? How about horizontal asymptote? Is there a horizontal asymptote? Yes, because the power, same power, right? Same power. So the leading coefficient is y equals 1, 1 over 1. So y equals 1, that's the horizontal asymptote. Okay, so that is horizontal asymptote. And then how about the y-intercept? What's the y-intercept? Okay, set x equals 0. Set x equals 0. Then what's the y value? So f of 0 is 0 over 8. Oh, sorry, negative 4 over 8. So negative 1 over 2, right? Okay, so this is negative 1 over 2. That's the y-intercept. How about the x-intercept? X-intercept, set the what? The other variable y equal to 0. Okay, y equals 0, that means set the numerator equal to 0. Because this is a fraction. Then the numerator is x plus 1, right? X plus 1 equals 0, so x equals what? Negative 1. So the x-intercept is negative 1 and 0. So when x equals negative 1, it's 0 over here. Okay, how about 4? When x equals 4, there's no y value. Okay, there's a hole. All right, then. Okay, x minus 1, x minus 2 is first power. So based on this vertical asymptote, one is above the line and one is below the horizontal line. But look at this. Since we have 2 points in the y-axis and x-axis, the graph should be connecting these 2 points, right? Looks like this, right? So the other one should be on the other side like this. All right. But in this case, when x equals 4, okay, if x equals 4, then what is the y value? Then if x equals 4, let's check it. 5 over, so f of 4. In this case, f of 4 equals what? 5 over 2, right? 5 over 2. So 2.5, something like this. So this point. So there is a hole over there, hole. There's a hole, like a hole. And the location is when x equals 4, y equals 5 over 2, 2.5. Make sense? So that's the graph. So when there's a common factor, we can remove it, but make sure there is hole at that common factor. Okay, next example is an application part, but this one is really simple. Okay, already the average speed is given. S of x is the average speed. And then there are two speeds. One is, 12 miles, 30 miles per hour going, 12 miles distance. And the other one is x miles. And this x mile is the distance with traveled at 60 miles per hour. So since the speed is given like this, we want to find the distance x that was traveled at 60 miles per hour. All right. And then let's say if the average speed is when the average speed is equal to 50 miles per hour. So this is given. So we will set 50 is the average speed. Then write the equation. And then from this we will find x. So cross multiply. Then 12 plus x equals 50 times 2 over 5, 1 over 60x. So, 12 plus x equals distribute, right? Then this will be 10 plus 2 is 20 plus 5 over 6 x. All right. So put x's together. All right, then x minus 5 over 6x equals, put 12 together and 12 to the right. And then from here, 1 over 6x equals 20 minus 12. So from here, x equals, 1 over 6 equals 8. So that x equals 48. So 48 miles. So if he drives, drives 48 miles with the speed, 50 miles per hour, then it satisfies the equation, right? All right, that's the answer. And then find the horizontal asymptote. So as you see this one, get the horizontal asymptote. What are we looking for? We check the degrees, right? Check degrees. So in this case, they are the same degrees. Same degrees. The horizontal asymptote is the leading coefficient, 1 over 60. So that is 60, isn't it? Okay, why is it 60? You should know this one. This means 1 divided by 1 over 60. So 1 multiplied by 60 over 1, right? So that is 60. So that's the horizontal asymptote. In this case, this should be, so the graph, something like this. If you graph it, it looks like this. So this is the speed, speed. And this is the, x values. The distance you traveled at 60 miles per hour. Then that's the horizontal asymptote, the average speed. So whenever you do it, if x equals 0, then y is 30, right? 30. So starting from this 30, it's increasing it. It's increasing, but getting close to what? Getting close. The average speed 60. So that's the horizontal asymptote. So the horizontal asymptotes of the graph of the average speed s is the line y equals 60. Right, y equals 60. So as this guy continues to drive at 60 miles per hour, the average speed for the entire trip will approach 60 miles per hour. So getting close to the 60. All right, so that's it for this example, and let's try the next one. Okay, here is a cylinder, and the radius is r, and the volume is given. Okay, from this one, write the surface area as a function of r. Okay, so in order to write a function of surface area, okay, let's make a net, the net diagram for this cylinder. Then it looks like this. So the column will be this square, and the top circle and the bottom circle is this, right? All right. So the length of the rectangle will be 2 pi r, which is the circumference of circle, and the height is h, and the radius of the circle is r, right? Okay, from this one, we need to rewrite h in terms of r, because we want to write surface area as a function of r. So we must have r instead of h. So anyway, using the volume function, so what's the volume of a cylinder? Is pi r squared, the area of the bottom, which is pi r squared, multiplied by h, right? And then the volume is given, so 21.6 equals pi r squared h. So we want to write this one in terms of r. Let's rewrite h. Then h will be 21.6 over pi r squared. So we can rewrite this expression so that h equals something. And then in this case, h is written in terms of r. All right, then what's the surface area? Okay, the area, let's say A. Okay, the surface area is, okay, there are 2 circles, and each circle is pi r squared, right? Pi r squared, there are 2 of them, so 2 pi r squared, plus the rectangle. Area of the rectangle is 2 pi r h. But in this case, we already found the h, right? We can rewrite this h so that the area is 2 pi r squared plus 2 pi r h. H is now 21.6 over pi r squared. So if we rewrite it, then the area will be 2 pi r squared plus, pi cancel out and 1 r cancel out. So the numerator will be 43.2 over r, right? So rewrite it. So put the denominator, same denominator, r, and then multiply the first term by r, right? So 2 pi r cubed plus 43.2. So this is the equation of surface area. All right. Then the letter B, okay, estimate the value of r so that it will produce the minimum surface area. Minimum surface area. So what is the graph of this one? In this case, use a graphing calculator. Okay, use a graphing calculator. And then graph it. And then if the graph looks like this, there's no, when r equals 0, of course there is no, this is vertical asymptote, so there's nothing. And then since the numerator's degree is greater, so there's no horizontal asymptote. It's got to be some different asymptotes. All right. And then the graph looks like this. Something like this. It looks like this. So the minimum surface area, it should be at this point, right? This point. So what's the x for this one? The x value. So that x value will be 1.509. Around this one. This is the x value. How about the y value? Then y value is 42.9 something. All right. So when x equals, so when x is, when r, actually this is r, right? When r equals 1.5 inches, then the surface area is around 42.9 cubic inches. So this will be the minimum. Okay, that will be the minimum surface area when the radius is 1.5 inches, approximately. Can you see it? Or in this case, we use the graphing calculator to find out the minimum surface area. All right, that's it. This section took long because there are so many definitions in this case. So we are at the end of chapter 3. So hope you study solve as many examples to get familiar with this type of graphing, graphing rational expressions. All right, that's it.